is with immense joy and pride that I welcome you to the 81st section of UL Space Club webinar series, a dynamic platform bridging scientific curiosity with cosmic exploration. Let's begin by extending our deepest gratitude to Sri Ike Kutisar, founder and mentor of UL Space Club, for his unwavering commitment and inspiring leadership. We are honored by the continued guidance of Sri Jairam Sir, former director of ISRO, whose presence and mentorship inspire every budding scientist and space enthusiast. A warm welcome to our esteemed guest and ISRO veteran. Your contribution to India's space journey motivate the next generation of pioneers. I would also like to acknowledge our dedicated core team, Mr. Varun, team lead, Mr. Abhinath, senior student fellow and curation coordinator, and Mr. Adarsh, webinar and curation head. Your efforts strengthen this platform with every new endeavor. Today, we are excited to welcome Mr. Paulose Thomas, founder of XPT online classes and lecturer in physics, as our distinguished guest. With his expertise in physics and passion for science promotion, he will take us through the fascinating topic of parallel world and cosmic code, exploring the mysteries of the universe and unlocking new perspective. This topic is particularly relevant in today's era of space exploration, and we're sure we will find Mr. Thomas' insight thought-provoking. And we will have an interactive Q&A session later. So, jot down your questions and be ready to engage. And I'm also delighted to welcome Sri Shajil Yuki sir, who will be moderating today's session, adding immense value to this academic gathering. To attendees, your enthusiasm and participation fuel this learning ecosystem. We encourage you to engage wholeheartedly, share thoughts, and participate in the interactive Q&A session. Without further delay, let's pass the baton to Sri Shajil sir to introduce our speaker and begin this stellar session. Thank you and welcome once again to UL Space Club webinar section 81.
Thank you, Srinivaswa, for your formal commencement of our 81st webinar here. We have been gathering here for the past 80 weeks, second Saturdays for our children. And the enthusiastic students, teachers, and the other veterans from ISRO is supporting, and with their blessing, we are continuing this journey of sharing knowledge from different aspects of science, and including space and other areas of science, the STEM and space angle. Today we are here with an interesting and curious subject, that is the parallel world and cosmic codes, and a little bit hypothetical or a little bit theoretical or a little bit philosophical. We'll hear the interesting story of our universe and the wonders there. And today we get an eminent speaker, that Mr. Paulose Thomas is a founder of SPT online classes and lecturer in physics, science promoter, and he is a postgraduate in technology in power electronics enterprise. And he has been the guest speaker at government and private engineering college, and is the TBI member in IT Calicut, and also postgraduate degree in power electronics enterprise, and awarded with the gold medal by Chancellor Vishwanathan for being the best outgoing student engineer. So anyhow, we are so glad to with your presence, sir, Paulose sir, and our Kutisar, the founder and mentor of UL Space Club, will soon join with us. And in the last week, we made a book release of E.K. Kutisar regarding his life with children and in ISRO. I proudly present that book here for the viewers. It's our Kutisar's book published by Madhrumi Books, and it is ISRO's ISRO Ile Kutikalam, and that's being accepted by the teachers and the students and the parents with their immense pleasure and great enthusiasm, and they are looking into these books, and we are proudly presenting it here. And I welcome all the veteran scientists, ISRO, the students and teachers who gathered here, even in between this examination time. And I proudly invite Mr. Paulose Thomas, who is going to present these curious subjects. And in support of that, this questionnaire session will be Gautam and Rishika will handle. And what of this that is in behind, there is Adarsh. And I once again welcome Mr. Paulos Thomas to this forum of UL Space Club for spreading his curious story regarding parallel, right, parallel world. Okay, thank you. Welcome, sir.
Am I audible, sir?
Okay. It's okay. Welcome. Sorry.
Thank you, Shizil, sir, for giving me a wonderful welcoming. Respected Cookie, sir, dignitaries, teachers, friends, a very warm good afternoon to everyone. So, Adarsh actually sent me a PDF regarding the previous webinar talks. And I was wondering, by looking at every single topic, that almost most beautiful topics are almost covered. So I was thinking, what can I say something different in front of you people, especially you all are, curious brain, I would say future scientists, and like which topic I will deal with. So I was just going through several topics, and when I look at black holes, that is already presented. When I look at Big Bang, that is there. Almost all the topics are almost covered. So I thought, okay, fine. Let's say something different, something more about which is not yet discovered. That could be something curious, isn't it? So before jumping into the topic, I would like to, I was just going through Instagram Reels, and one of our colleges recently conducted a program based on, something useless, make projects something useless. So that was actually interesting. The title itself was very interesting. I don't know the exact quoting of that or framework of that title, but it was very fun. Like students are actually building some useless works. Now you might be wondering, like, what is the big deal, or what is the big use if you make a useless product? Now, for that, actually, it's not easy to make something useless. This is something that you need to understand, that the brain, how it works. Normally, it solves for problems and it tries to find some solutions. Okay. And then when you make something useless, you need to use a little bit more sharper brain. And one among the works was like, there is a waste bin, and whenever you try to go and put a waste into that waste bin, it will close. That was actually funny, but to code something like that and to close the opening of that waste bin whenever you try to actually put it, it's something interesting. One more thing I want to say before jumping to my talk is regarding a restaurant that is, working in Kerala. I don't know the exact name of that. It's a hidden restaurant. Okay, so recently in the Instagram I saw that, and it is hard actually to find that restaurant. Okay, number one. And once you go into that restaurant, you will find very difficult to find waiters. You will find difficult to see the menu. And once you order food, and then you will get the food, and once you start eating, once you are done, you will find difficult to, you need to actually go and search for the washroom. And by the time you wash your hands and when you come back, even the plates and everything will be disappeared. So people are thinking differently. So that's why I started my talk with this introduction. You need to think differently in order to solve some mysteries in the universe. Okay, with that introduction, let me share my screen to my presentation. Just let me know if you can see the screen once I share. Can anyone tell me if it is visible? Great. So the title of my presentation is Parallel Worlds and Cosmic Codes, Unlocking the Secrets of the Universe. So most of the slides that you're going to see is something related to, obviously, as our sir introduced, it's something related to hypothesis. What has hypothesis something to do in science? You need to understand that it is from the hypothesis that we actually make a theory, and It's basically the hunt of hypothesis that every science enthusiast will be doing. The hunt of evidences for a hypothesis. So I thought, okay, there are several hypotheses, which is something not being much discussed. So let's go through a few of them and let's evoke our brain and start solving them one by one through different techniques. So first, I decided to split this presentation into 3 or 4 parts. The first part, I'm going to show you the key cosmic mysteries that you will see through this. I mean, not all the mysteries, but only 3 or 4 mysteries I want to introduce you. Maybe few of you might be already knowing it. Few of you might not have a much good idea about it. So let's see the very first cosmic mystery. Okay. So the first mystery I wish to say is regarding the observable universe, the size of the observable universe. Okay. Now, whenever we go for debates, public debates and talks and these kinds of programs, this one question always stands out. Like, what is outside that universe? What's outside that universe? So that question itself, whenever you frame a sentence and put a question mark, that is not necessary to be always a question. I mean, it is not necessary to be always logical. For example, what is the color of the electron? That question itself, even though the sentence is coming after a question mark, you need to actually check whether is there any logic for that question or what happened before the Big Bang. So like that, one question is, what is beyond our universe? So, well, we know the size of the observable universe. That is the only fact that we do know. And beyond that observable universe, actually we have no clear idea regarding it. We know something that the age of the universe is 13.8 billion years. This number you might have seen several times through these 81 webinar presentations. But again, just reminding you some key numbers. And if that's the case, the radius of our observable universe should have been this 13.8 billion, light years. But it is not. We know that. The actual radius comes close to 46.5 billion light years. So what could be the possible reason for this? And I hope all of you know that the universe is not static, it is expanding, isn't it? It's an expanding universe in an expanding universe that we are living in actually. Okay, so the universe keeps on expanding. So what we can see up to is maximum the observable universe is the radius is up to 13.8 billion light years. So the question comes like, what is happening beyond that? Is there any other different universes out there? Or is the physics working differently out there? Isn't it? Normally, we always use too many mathematics in physics, which is obviously required because the language of the physics itself is mathematics. But, in physics classes and all, whenever I go and teach, students always say that this point that it has to be something more curious. Like we do study, 14 plus 14, 28 chapters in NCERT in 11th and 12th. And then, for them, it is very boring. Like, it's the same thing. It's so much mathematics into it and students are not getting marks. Physics is, becoming their difficult subjects or boring subject. So what we need to do, okay, like if you are planning to become a teacher in the future, or if already teachers are there, is you need to put the best word is masala, but you need to put some scientific masala into it. Say something about the universe. Say something. Let them think what is beyond the observable universe. So this is one question that you can actually ask students and you can wait for their curious, beautiful answers. What is actually beyond it? Or are we actually inside a black hole? Is this entire observable universe, can we treat it as a black hole? These kinds of questions are very interesting, isn't it? Another curious thing that or mysterious thing is regarding none other than the beginning of the universe itself. So many people still even, debate like the origin of the universe, regarding the origin of the universe. Let me clear one single thing in that Big Bang doesn't explain about the origin of the universe. It explains about the expansion of the universe. Now, this is one common mistake that many people used to do, say, like Big Bang is actually the origin of the universe. Everything came from that, something called nothing. And that nothing itself is contradictory. We debate on that word nothing. So many things happen there. But what we know according to the data is the Big Bang is all about how the sudden rapid expansion of universe. So inflation followed by accelerated expansion. How did all this universe expanded into this what we see? This is what actually Big Bang is explaining. So the question comes, like, what is beyond that point of that initial mark? Like from what we know onwards, we can put a mark there. Okay, we can put a reference there, and after that reference, we know everything. And before that reference, we don't know anything. So what actually happened before that reference? You can call it like blank time or something like that as that reference point. So was there any other, another universe which was trying to crunch towards that single point, and again a bang started and our universe formed from that? So these hypothetical questions come from there. It's actually beautiful to think about what actually is the previous state of that reference point, isn't it? So think about it. Think about what actually happened before that Big Bang point. Another mysterious thing is regarding the forces of the nature, isn't it? Fundamental forces, what we call as, it was there in the 11th grade, very first chapter. It's now deleted. That chapter is deleted, called Physical World. And those description about that 4 fundamental forces, I always think like, why did the government took that chapter off? Because that's the only chapter which will give you an idea about the 4 fundamental forces. And none other than we know strong nuclear force, electromagnetic force, weak nuclear force, and gravitational force, isn't it? A theory of everything is a hypothetical concept again. This is another mysterious concept, okay? And the hypothesis is like this, like all the fundamental forces were actually at one single unified force at the beginning of, or at the starting of the Big Bang. So that's the hypothesis. So I'm repeating it. Most of the things what I'm trying to say is basically hypothesis, which we don't have. We do have mathematical explanation for many of those, but we don't have observable evidence for it. So always remember that. You just don't go and share to someone that I heard a fact that all the 4 fundamental forces are one single unified force at one time. No, that is a straw man fallacy. I didn't say that. I'm trying to say is that these are hypotheses which we are going to discuss in today's session. Okay, so it's interesting that we have already combined electricity and magnetism together to electromagnetism. Okay, and we combine this electromagnetic force and the weak nuclear force to electroweak force. So that part is already done. We have done that. Okay, and we have proved that in Large Hadron Colliders that electroweak force actually do exist. Okay, and strong nuclear force is there on the other side, which we are trying to combine it with the electroweak force, and mathematically we propose an idea of grand unified force. So like that, we basically combined weak nuclear force, electromagnetic force, strong nuclear force to a grand unified force, hypothetically or theoretically. Now, on the other side, we have gravity, Einstein's gravity playing a key role, like special relativity. Put some gravity into it, you get general relativity. And then general relativity on one side, and on the other side, we have grand unified force. Somehow we need to bring them together to get that beautiful theory of everything. Because whenever we do the numerical problems, we see gravitational force, one formula. Okay, electromagnetic force, another formula, isn't it? Or electrostatic force, yet another formula. We study different formula for it. What if you have one single formula and you can put all these cases and you get different results from it? So that is one proposal that string theory or M theory or superstring theory has put forward, where it combines all these 4 fundamental forces. Once again, I have hypothetical concept where all the forces are unified, and a beautiful theory of everything is what superstring theory or M theory is proposing. Okay, so that is regarding theory of everything. Another mysterious concept, maybe, recently many of the people do love this topic of dark energy and dark matter. Just give me a minute. Right. Okay. So the mystery of dark matter and dark energy. Okay. We know that the universe is actually steaming up with things around you, right? We can see galaxies out there, we can see stars out there, we can see planets, comets, meteors, meteorites, moons. Everything, will come up into that 4.9% ordinary matter. So there comes the question, okay, fine. Almost 5% of the universe, what we see around us, we know about it, we have an idea about it. What is the remaining thing? What is actually that remaining stuff inside the universe? And we split it as dark energy and dark matter, isn't it? Dark matter, in simple language, we can say that something like a glue that brings all the stars within a galaxy together instead of throwing it out when the galaxy spins. And dark energy is something that helps the universe to expand. I mean, space itself to expand. That is what dark energy will be doing. But we don't know what these things are made up of. And obviously, we are in search of it. So the 68% of our universe is basically dark energy, 26.8% is dark matter, 4.9% is ordinary matter. So again, people do argue that actually we don't know anything about dark matter, we don't know anything about dark energy. No, it's not like that. We have figured out so many things regarding dark matter. Okay, we have also understood a lot regarding dark energy too, but there is a huge arena that we need to explore to understand what this thing actually is and how it interacts with the ordinary matter. All these things have to be understood. Okay, so these are the 4 key mysteries, cosmic mysteries, that I wish to introduce before you. So think about these things. Like, what are they actually, what we can actually do to solve these puzzles out? Now, one more thing let me just quickly tell is regarding black holes. Well, obviously, you might be so fond of the movies like Interstellar and anything that related to black holes, gravity, etc. And this is one among the largest black holes that we do know. It is TON 618. Look at its radius. Just think about this. Just think about that number. The radius of that TON 618. It's 1,300 astronomical units. How huge it will be. Think about it. What is one astronomical unit? We can say that one astronomical unit is the average distance between the sun and the earth. Average distance between the sun and the earth, that will come close to 15 crore kilometers. So times 1,300. How big that will be? That is the biggest black hole that we have spotted out on 618. So what will be such a black hole will be looking like? How does it look like if you go into that black hole? So all these questions, I'm putting more questions than answers. So it will be something different that you might be thinking about. And every day we see things around us. Normally, very few students or very few people nowadays look at the stars, isn't it? Now we are all looking down instead of looking up. Looking into mobile phone, or instead of looking up, we don't normally look stars, and we don't enjoy the night skies nowadays, right? Think about it, like a dead star, so massive, okay? Something like this size. What will be happening inside such a thing? Okay. Now, this is the second part of the presentation, which is string theory. I just want to give an insight regarding that hypothetical concept of string theory. It is actually interesting, okay? Because you might be knowing regarding gravity, you might be regarding knowing electromagnetism, maybe a little bit concepts about strong nuclear, weak nuclear forces. But what if you bring all together into that one single unified theory called string theory or superstring theory or M theory? It's actually 3 different things. I'll just want to show you how they are different. So to give you an introduction about string theory, let me take a glass of water and pour some water into it. And we know that all these matter, what you see around you, is made up of molecules, and these molecules are made up of atoms. And this is not the best picture to show how an atom looks like, but let me bring it more curiosity into it. I mean, atom itself, you can take it as a different webinar session, isn't it? How it looks like. Anyways, forget about that. Now, within an atom, we know electrons are there, nucleus is there. Within nucleus, we know protons and neutrons are there. And let's go deeper into it. How many of you actually know that protons and neutrons are actually made up of quark particles? Quarks. These quarks, if you look at one single quark, there are different types of quarks, okay? And one single quark, if you take it, it is basically a net sum of 3 valence quarks. Net sum of 3 valence quarks. That's the word that I wish to use it. And if you look at the mass of the one single quark, and or we can say, let's call it a proton. If you take the mass of the proton, and if you compare with the mass of these 3 valence quarks, you can't even compare it, because you can see that the mass of the 3 valence quarks is much lesser than we actually think. So who is actually contributing to the mass of the proton other than these 3 valence quarks? So there comes new and new particles. The interactive forces between these quark particles is actually contributing to the mass of the proton. It's actually a very interesting area. So let's keep it simple. Matter made up of atoms, and atoms are made up of proton, neutrons, and electrons. Protons and neutrons are basically made up of quarks. So whenever you reach at that question, normally we think the next question like what it is made up of. So we had no clue about what quarks are actually made up of, so we call them as point particles. This was the best way to solve many things. Consider things like point particles. If you don't know about what is actually quark made up of, treat them as a point particle. Because even after treating quarks as point particles, the present day physics works. Understood? Like quantum mechanics that we are dealing with now, it works if you treat quarks as point particles. It works beautifully. Okay, so still that question is the right. What is inside the quark? So these are some the particles that we do know, which we have ordered them into the standard model of elementary physics. These are the things that we do know, like what matter is made up of. Are there any new particles? Well, we don't have much clue. But these are the things you can see. That's very small table physics people do have compared to chemistry people, like a periodic people. We don't have like an elaborated one. We have a very small table. And using these things, the entire matter is made up of. So the question, what is inside the quark? And that is where string theory is coming. That string theory proposes an idea that these quarks are made up of vibrating strings, one-dimensional strings. It can be closed loop or open loop strings. Vibrations, energy vibrations. So treat strings as energy vibrations in 1D. Understood? So now we can say atoms, jumping to nucleus, protons and neutrons, quark particles, and then none other than strings. So once again, a hypothetical concept, strings. So the problem with these strings is, in order for these strings to exist, we need some extra masala that is called higher dimensions. So if only these higher dimensions do exist, you can actually prove strings do exist because they are interconnected. So the word dimension, isn't it? That higher dimension, when we say about higher dimension, we always, the first thing that our brain will do is that it will connect to some movies, isn't it? So what are actually dimensions? So let's start from a 0th dimension. 0th dimension means actually an infinitesimally small point. Even that orange dot is having a width and breadth, but that should be there. It should be a very, very tiny point. should be an infinitesimally small point, then you can call it as a zeroth dimension. Okay. Now, such a zeroth dimension, you pull it out in its perpendicular direction, then what you get is actually a single dimensional straight line, one-dimensional straight line. Okay. And such a one-dimensional straight line, you pull it in its perpendicular direction, you get a plane or two-dimensional plane. Okay. And such a two-dimensional plane, if you extend into its yet again its perpendicular direction, you get a three-dimensional cube. Okay. So this is all actually what we know till the third dimension, right? Three spatial dimensions, we have a very good idea. Fourth dimension, normally we consider as time. But what if there is a fourth spatial dimension? What if that question is coming? What if there exists a fourth spatial dimension? And here we have the fourth spatial dimension, a proposed concept called tesseract, which definitely I'm sure that you might have seen this in especially movies like Avengers or some other movies. I'm not sure about in which other movie tesseract is shown, but yeah, fourth dimensional tesseract. But let me give you something, an insight about actually how much or how many dimensions human beings can actually see. It's only actually up to 2 dimensions, not up to 3 dimensions. It's our brain that perceive you and it will trick you and tell you that what you're looking at is a third dimensional object. Actually, brain can see maximum up to 2 dimensions. Imagine there is a box in front of you, which has a length and a breadth. Also, it has thickness, but when you look right from the front side of it, you cannot see the thickness, isn't it? To measure the thickness, you need to actually look from one side, and then you will see its thickness. Then you will understand it's a 3-dimensional object, isn't it? So brain can actually see only up to 2 dimensions. And it is our experience that is teaching you that, okay, the object right in front of you is a 3-dimensional object. Even the picture, what I'm showing you is the 2D projection of a 4-dimensional tesseract. It's not even a 4-dimensional object right at what you're looking at. It's actually the 2D projection of the 4-dimensional tesseract. Understood? So imagine what if you can extend these dimensions into more than 4, 5, 6, 7, and up to 26 such dimensions. If you can push that up to 26 dimensions. Whether we will understand all these things, I don't know, but string theory proposes that many higher dimensions. So to make things easier, imagine you have a violin and you are playing that violin and beautiful notes from that violin is coming out. Each note, you can take it like a vibration. Each vibration, you can compare it like a string. Okay, so every time you play a note, it vibrates in one particular frequency. So every kind of note what you hear from a violin is basically a kind of vibration. So string theory is telling that, okay, well, every single fundamental particles is basically a vibration. Like you can take photon, it's a vibration. You can take electron, it's another vibration. You can take maybe neutrino, it's another vibration. So according to string, all these fundamental stuffs are vibrations of different frequencies. And with that, string theory, thus, it has 26 higher dimensions and it shapes something looks like this. We call it Calabi-Yau manifold. That's the shape of the strings which is proposed by string theory. So interestingly, these scientists actually started to draw the shape of the Calabi-Yau manifold. They did the calculations and it was coming many, many shapes and it was not even stopping because each shape can actually propose a universe. So the number of shapes is actually a proportional count to the number of universes. And do you want to hear that number? Like how many shapes we have figured it out? It's close to 10 raised to 500 shapes. 10 raised to 500 is an extremely huge number. And those many universes is what string theory is proposing. 10 raised to 500. Is it really crazy? Yes, that is what string theory is proposing. So scientists found like, okay, well, this is going too hypothetical. We need to do something. Definitely we need to do something. And we need to reduce the number of these dimensions. And thus they brought superstring theory. So according to this superstring theory, which is yet another hypothesis, which is an extension of string theory, it needs only 10 higher dimensions. So 9 spatial dimension and one time dimension. Whenever I say higher dimensions, the total number minus 1 are basically spatial dimensions. So here 10 higher dimensions means 9 spatial dimension and 1 time dimension. The superstring theory, okay, scientists brought this superstring theory in 1960s and 70s. And the problem with this superstring theory is that whenever you need something new, you need to bring some new concepts. Like for string theory to exist, you need higher dimension. So what should be there for superstring theory to exist? And we need supersymmetric partners. More and more problems, isn't it? Now you need to hunt for supersymmetric partners. So, well, what are supersymmetric partners? Well, I already showed you a table of standard model of physics. That's what you see towards the left side. Imagine every particle in that standard model has a higher energetic supersymmetric partner. Okay, just imagine. So gluons, we know its supersymmetric partner is gluino. Photon, if we know about photon, just imagine there is a supersymmetric partner called photino. And it goes on. So if there is a supersymmetric partner for every existing particle in the standard model, then supersymmetry exists, is what we are saying. If supersymmetry exists, then these 26 higher dimensions, you can literally reduce it to 10 higher dimensions. But when you bring supersymmetric partners, new problems arise. And that new problem is 5 such stable supersymmetric theories or superstring theories will immediately come into the picture. 5 superstring theories will come into the picture. So again, well, we won't stop there because mathematicians and physicists will never quit there. Okay, fine, it's a new idea, it's a new problem now. We need to solve it out. And they decided, okay, let's combine all these 5 superstring theories, okay, with some amount of extra, gravy called supergravity, and altogether they named it M theory. M stands for, actually, there is no specific name for that M. You can call it as membrane, you can call it as mysterious, you can call it magical, because we don't know what actually M stands for, because first of all, it's a huge hypothetical idea. But whatever, if M theory to exist, okay, you need 1 extra spatial dimension to it. So 10 spatial dimension and 1 time dimension together, it's M theory, which is what I actually see at the top of the table a few slides before. The theory of everything slide, if you do remember, at the top, you see M theory, which is one among the proposed idea of all the existing fundamental forces. The accumulation of all the fundamental forces brings you M theory. Think about this. Just think about for a second, like if M theory is the actual reality, straight away higher dimensions do exist, straight away parallel universes exist, straight away multiverse exists. How interesting it would be. But what if they don't exist actually? What if M theory is completely wrong and some new theory might be the actual core concept of it? Well, we don't know. That's exactly why I'm bringing this hypothesis in front of you. Just work it on it. What happens if someone of you actually resolves these puzzles, isn't it? So that is regarding M theory. So what is the best way to figure it out? Or to, well, we do have the math. Beautiful mathematics is there supporting it. It's not just some simple fictional stories, okay? Don't think like that. We do have beautiful mathematics to support every single slide which I said. Every single slide, there is a strong mathematics behind it. The question is, we don't have observable evidences for it. How we can actually bring some observable evidences? Because science means, it has to be scientific, isn't it? This is very important. Everything has to be scientific. If you say that some Jabambu alien exists, then you need to show the proof. Whoever is claiming it should bring the proof, should bring the evidence. This is something that I need to share it to you for today. That if you are claiming something, you need to bring the proof. And when you bring the proof or evidence, it has to be repeatable in order for it to be scientific. This is very important. So how we can prove these theories like M theory, string theory, superstring theory? Well, one clue lies in the particle accelerators. Particle accelerator, I hope you might be already knowing. Large Hadron Collider is a very one good example for particle accelerators. But the energy of every particle collision in that is actually limited. Okay, so the problem is, in order to find these supersymmetric partners, we need huge particle accelerators, which we are actually planning to build near to LHC itself. But the thing is, it will take a long time. But imagine such a future circular collider actually exists. And then we turn on the machine and then let the protons collide with immense amount of energy. And then we are observing it using extreme powerful computers. And then you get one supersymmetric partner, maybe photino or maybe gluino. Just imagine, like we discovered Higgs boson from Large Hadron Collider. What if actually a supersymmetric partner exists? Immediately, supersymmetric partner, if it exists, superstring theory is proved. Superstring theory, if it is proved, immediately you can climb to many higher dimensions. Okay, so this is one way that we can discover, the higher dimensions, whether they do exist or not. So a quick nutshell of the string theory is like, okay, molecules are made up of atoms, which are made up of protons and neutrons. They are made up of quarks, and quarks are made up of strings. Every vibration of a string, you can treat it as an elementary particle, and the shape of the vibration determines the number of universes and the fundamental constants. I'll come into fundamental constants later. And string theory, for it to exist, you need 26 higher dimensions. So we decided to reduce that to superstring theory. The problem with superstring theory is that you need supersymmetric partners. Such 5 superstring theories do exist. So some amount of supergravity also you put into it, you get M theory. M theory, the problem with that is, if in order for M theory to exist, you need extra one dimension. And this altogether, presently, we propose the theory of everything concept with 11 dimensions, with 10 spatial dimension and 1 time dimension. From where will you get the evidence? We have particle accelerators for that. Now, the last part of this entire presentation is all regarding fine-tuning of the universe. Fine-tuned universe. This is something, recently I had to debate with on many platforms regarding the fine-tuning part. Maybe it might be contradictory. Maybe you might not actually stand with my position. And that's absolutely fine. This is yet another hypothesis which I'm going to keep it in front of you, the concept of fine-tuning. So what is actually fine-tuning, or what is fine-tuned hypothesis means? So the statement goes like this, that idea is that the fundamental physical constants and laws of nature seem to be, okay, now I need to actually highlight it, seem to be precisely calibrated within a narrow range that makes it possible, makes life possible. So the concept is, we are living in an earth where obviously life is possible. And look at the position of the earth. It's in the Goldilocks zone. Wonderful. That's why, because life is there. And you look at the constants like gravitational constant, charge of electron, speed of light, mass of proton. These are constants, fundamental constants that we are talking about. It seemed to be precisely calibrated, something like designed. So straight away, these questions will come like, is there actually a designer behind these fundamental constants? Is there actually we call it as an alien that has actually designed this entire universe? Or are we in a simulation? These 3 questions immediately come. Like, seeing this precisely calibrated numbers, do we need to actually follow any of these three. So the key questions based on fine-tuning comes like this. What are these fundamental physical constants? So just to give you an idea about fundamental physical constants, we do have 26 fundamental physical constants that we have observed. Maybe more will be there. And we believe that the entire universe is, the basic building blocks of this universe, or the physics that we rely upon, are these 26 fundamental constants, which I will show in the next slide. That is basically what I mean by fundamental constants. So when you look at these fundamental constants, the numbers are beautiful. It's like you see the fine structure constant, it is 1 by 137. Any change in that fine structure constant can bring some changes out there in the universe. You change some part of gravitational constant, you change the value, something else may happen, like maybe a slight increase in the gravitational constant value may basically bring the galaxies together, and it may go for a big crunch. A slight decrease in the gravitational constant may not even form galaxies. So fundamental constants are very, very interesting part. Now, that's the first thing. Second thing is, what is anthropic principle? Whenever you hear the fine-tuning concepts, you may hear this word, anthropic principle. Means, well, we are existing here, okay? We are existing here according to anthropic principle. We do exist here, and hence we are measuring all these things, what you see around you. Basically, there is an observer. And if there is no observer, there is no measurement. Okay, so you need an observer to measure all these things. And if there is no observer, the existence of universe itself doesn't make sense. That is one idea about anthropic principle. So fine-tuning people, those who support fine-tuning say that, well, the entire universe is there just to keep you alive because you need to measure it. Now, whether it is logical or not, that's up to you. I'm putting that question right up to you, whether it is logical or not, that you can decide. But the third point is that if the constants were even slightly different, what would happen to the stars, the chemistry, and the biology that we see around us? A small change in these things, the electromagnetic force, if it changes slightly, then how electrons do interact, how electrons and protons do interact. It's a question, right? Whether atoms do form. Think about it. The last question is like, is fine-tuning the evidence for design, chance, or necessity? Means, actually, whether it is designed or not, do we have evidence to counter argue that? Or is it just a chance? Or is it actually necessary for all these things to exist? So one among the most very philosophical questions, isn't it? So let's look at the fundamental constants. You can see several fundamental constants here. I'm not going into one by one, but just giving you an idea about what I meant by fundamental constants. The mass of many particles like quark particles will come under fundamental constants. Understood? So you can see the cosmological constant there, Higgs boson mass coming there, okay, fine structure constant coming there, etc., etc. So what are the best solutions that you can give to these arguments? Like something against the fine-tuning. Like if someone is telling, okay, everything is designed just because some kind of extra intelligent species or extra intelligent designer or alien, whatever you can call it, or the word God itself, you can say, has kept you out there because you need to observe all these things. If that is how the statement is coming, then you need to bring the solution like, well, multiverse hypothesis. Okay, fine. The counter argument to fine-tuning goes like this. Okay, you see a universe with 26 fundamental observed constants with these numbers. What if there is another universe out there? Okay, what if another universe is out there with some different fundamental constants? What if a third universe is out there with yet another third set of fundamental constants? So everything comes straight away into a probability, isn't it? So this universe is existing with these fundamental constants is just a chance, is one argument against fine-tuning, because several such possibilities do exist in parallel. So that is one concept of multiverse. The multiverse hypothesis itself are 5 to 6 hypotheses. I'm not going deep into it. Quantum multiverse is the several types of the one more I will just want to show you, like parallel universe. It's another kind of multiverse. Like every quantum measurement is observed or measured. Okay, every time you measure a quantum function or quantum operation, then the universe will split into two. It's a kind of many world hypothesis. It's very interesting. Imagine you are in this universe, you are, proposing a girl, and that girl in one university is rejecting and another university is accepting. So the universe keeps splitting into, it will break down into several small, not small universes, but parallel universes. And that is the beautiful concept of parallel universe. So we might think, okay, come on, whether all these things actually exist? No, this is just to give you an idea, like how these quantum functions actually do operate. Okay, so the thing is, the concept of multiverse is very, very interesting, and there are several types of such multiverse hypothesis itself is there. So you can even ask questions based on these multiverse hypotheses, like what are the different types of multiverses? Can we actually test these multiverse? Or can we ever access or prove these higher dimensions? Or are we actually living in a simulation? Well, there are many techniques. Once again, many techniques, and we are actually trying those techniques. Okay. Well, we don't have any single evidence to prove that multiverse exists. But this is one among the best counter argument against fine-tuning. Fine-tuning itself is a hypothesis. If someone has designed what you see around you, immediately the first question that you can ask them is, okay, well, if some kind of intelligence designed this universe, who designed that intelligent species or that intelligence itself? So if you're speaking about design, well, that thing also requires a particular design, isn't it? So think about it. So if an alien species has designed all these things, what you see around you, who designed that alien? So it's an infinite regress problem. Immediately it will go to an infinite regress problem, which will never end anywhere. Okay, so these are the questions that can be asked based on the multiverse hypothesis. What are the possible methods to test it? That will be interesting, right? That is because when you use the word testing, experimenting, that comes to science. We'll come back to the science. So we do have a cosmic microwave background radiations, and any anomalies in this CMB radiation, we can figure it out. And it could be the potential multiverse signals. It could be, who knows, in the future that we figure out maybe if at all some multiverse exists and you get the signals from the CMB and radiations. Another possibility is that, black holes and their connections to higher dimension, figure out the problems related to black holes. Well, we stand just in front of the event horizon of the black hole, and we are completely unknown about like what actually happens inside it. Well, so many hypotheses are there regarding what is inside black hole. Maybe you jump into a black hole, you pass through a wormhole, you jump out from a white hole. So many interesting concepts are there. So try to solve the problems regarding black holes. Maybe you may get some idea about multiverse there. Another option is like Large Hadron Colliders, trying to find some supersymmetric partners by building huge particle accelerators, which is one option. Or try to detect the gravitational waves and try to study it based on those gravitational waves, because what the thing is, everything that you measure outside the Earth is based on light. Now, other than light, what we have only one option is gravitational wave. As I said before, that our observation stops at 379,000 years after the Big Bang, because that's the point when the photons became free. So that's why you see that CMB radiation out there. You have no access to see what happened before that, that cosmic microwave background, what is actually behind it. The only one way to figure out is gravitational wave. So if you can detect the gravitational waves, you may further go into that Planck time moment. Understood? Now, resolve the problems regarding quantum entanglement, dark matter, dark energy, etc. What if someday you can actually detect a multiverse? Just think about it. So I just want to conclude my hypothetical presentation with few points. The first point is the universe may appear fine-tuned, but what we call tuning might simply be the natural outcome of physics we don't yet fully understand. Okay, so we don't have any evidence to say that something is fine-tuned. We don't have any evidence. You look at the human body, there are so many errors, so many flaws in the biological evolution. You look at the chemical evolution, you look at it, that means the very first life, how it might have come. We don't know. Well, there are hypotheses like that. Okay, so from some chemicals, when they come together and forming the very first life, think about it. Think about that hypothesis. Errors are happening there also. If it is a properly designed universe, a properly designed stuff, these kinds of errors won't be there. You look at the position of the earth, you look at the earth itself. Is the earth the best place to live? Do you really think so? Just imagine about the landslides that are occurring, the tsunamis that are happening. And look at the land area where actually people are living. That's a very interesting thing. Okay? Almost only less than 3% of the land area actually human beings are staying. The remaining percentage basically goes for oceans, seas, deserts, forests, Arctic, Antarctic, volcanic areas. The remaining portion is where the entire population is actually staying. Do you think that Earth is the best place to stay? Do you think that actually an intelligent life or intelligent species will design something like this and call it intelligent? Think about it. The second point is the multiverse, the string theory, and the cosmic evolution offer us ways to explain existence without invoking special design, reminding us that nature is capable of producing wonders on its own. You can see that in the nature itself, from the abiotic life, how a first cell might have come. Think about it. The nature knows how to solve these things. We have a very valid proof about biological evolution. Okay, you can see how beautifully nature, figures this out, how it solves the mysteries. So, well, we do have a lot of lacks of evidences to say that, okay, how the life has evolved. I mean, after the first cell. How the first cell came, we don't know. But after that, how it evolved into the species that you see around you, we have beautiful evidences. The nature knows how to solve these trickeries without any, designer. The third concept is that rather than seeing the cosmos as made for us, we can see ourselves as products of it, born from its laws, shaped by its accidents, and curious enough to question them. So, well, one way we can say we are born here just by an accident, probably. Understand? Just by an accident, probably. Okay. So, well, anyways, we are born, so we need to live it. No doubt in that. So, let us be always curious and let's try solving the mysteries. And finally, let me conclude my talk with the last statement that the beauty of the science is that it doesn't settle for mystical answers. Never settle for mystical answers. It seeks deeper laws that may one day reveal why the cosmos is exactly as it is, without needing anything beyond itself. So keep this in mind, that as the final conclusion, that never jump into quick answers. Never jump into quick answers. Maybe we might stop at some point. We don't know what to do after that. Well, immediate conclusions we may come into. For example, you look at the night sky and you see something glowing. What do we conclude normally? Suddenly we conclude, yes, here we go, there is an alien going. Just because you don't know, you should not conclude that to an alien. Imagine if you're walking through the forest and then you heard some kind of noise, and then immediately you are afraid and you are concluding that it could be some kind of ghost. How many of you actually have walked through the forest every single night? Have you ever? No. So you don't know about that sound. So never conclude to that as a mystical answer. what you need to do is that you need to seek deeper laws behind it. What might be the actual cause of that noise? What might be the reason for that light? You need to think about it. So with all these hypothetical concepts in front of you, let me conclude this talk. Thank you, dears.
Thank you so much, sir. Paulose Thomas, sir, for such an enriching and thought-provoking session. As a sci-fi movie enthusiast myself, this was much like that scene in Doctor Strange in Multiverse of Madness, where Doctor Strange and America Chavez fall through a cascade of wildly different universes in seconds. And today's session has taken us on a similar leap through higher dimensions, cosmic structures, and the codes that might govern us. So, sir, as Carl Sagan once said, somewhere something incredible is waiting to be known. And I believe we have touched a part of that today. We have also received a number of sharp and curious questions from our participants during the session, each one reflecting a genuine desire to explore this subject further. So now let's open the floor to the Q&A segment and dive into some of those questions. May I, sir?
Yeah, sure.
Okay, fine. So the first question was asked by Adil Prajesh. So his question is, according to my research, our physics is made by humans. So it'll only work in our surroundings. It doesn't work at black holes and such things. So there is no need that aliens to be in a planet with similar systems, laws like Earth, similar to the parallel universe theory. There might be a universal law that connects physics and anti-physical things and such laws. What is your opinion on this?
Okay. Well, I'm trying to understand that whole statement. Okay, fine. It's basically a comment based on the parallel universe and the alien. Well, I just need to go through that one more time. Give me a second.
Sure, sir.
Okay, so basically there might be, the key sentence is there might be a universal law that connects physics and anti-physical things and such laws. Well, I like that word, anti-physical things, kind of metaphysics and all, But you need to understand that, well, the only way to explain things that are happening around us is only through science. So something unscientific, let's keep it aside because it just doesn't work. So whatever we are trying to bring in, it has to be scientific. That's the first thing. It has to be scientific. That anything out of science, we don't need to bring it here. That's the main thing. And yes, as you said, well, aliens may be there, may not be there. Inside black holes, again, we don't know. Maybe we might figure out later in future. Just think about 100 years back, what all things we have discovered. Was there any mobile phone? Was there any supercomputer concepts? Concepts might be there, but think about it. Actually, what all things actually existed. Now think about 100 years after this day. Maybe this presentation might be there at that time also as a reference. And whatever we do say, or the hypothetical concepts I put in front of you, might be reality at that time. Okay, so, well, my opinion is that, well, we need to bring scientific stuffs together, and then we need to resolve what we think as the hypothesis. This is what my personal opinion is. There could be several clueless stuffs out there, maybe beyond Event Horizon, before Big Bang, all these things. It's not actually unscientific. We have science and we need to explore deeper into this science and we need to figure out the stuff behind it. That's my opinion for that.
I hope the route is clear. I appreciate the clarity you have provided to him, sir. So the next question is also asked by the same person. It is, We consider the fourth dimension with time, but it may not be like that as we think. So we cannot actually create 2D and 1D, and we cannot even imagine a 0D. So, similar to them, fourth dimension may not be seen or created by us, but one thing, we are three dimensional and we can see all parts of 2D object, example, a square. But a 2D living thing cannot see similar to that. We cannot see the 6 phases of a cube in one look. But 4-dimension organisms can see. What is your opinion? And is black hole a 4D object?
Okay. Well, comparing to a 2D object, well, that is a right idea. Like, for example, an ant is crawling and then it stands in front of a tall tower. And imagine it cannot process the height. So what it will do is that it will be crawling around, right? So the maximum knowledge that it is going to get is an idea about the length and the breadth of it. But regarding the height, it won't be having a clear picture of it. So ant, well, it is a 3D object, but imagine a 2D living thing, just moving around in XY plane and then see something, a 3-dimensional object in front of it. It cannot process it same way. As you said, it is true that when you look, suddenly a 4th-dimensional object come in front of us, we won't understand, first of all, how it looks like. Imagine a 4th-dimensional object passing through our, realm, just like that, how we look like it. So we might see it like a sphere emerging out from nothing, okay, increasing its size and then decreasing its size back to 0. So this is how we perceive a 4th-dimensional object. We see it like a 3-dimensional object, even though we can only see 2D. We see it like a 3-dimensional object popping out from nowhere and then, increasing its size into its full scale and then popping out back into nothing. This is how we will be observing a 4th-dimensional object. So that is my opinion regarding 4D objects. And the reverse way, think about the reverse way. Like we know 2D objects, and 2D objects may see 1D objects. So what if 4D objects see the 3-dimensional world, like where we are living? What if there are 4th-dimensional beings looking at us and, simply laughing at what all, stupid things this guy is telling, that we are telling about the 4th-dimensional objects, so species. But the thing is, even if we do say some like we put a hypothesis just like that, if there is a 4th-dimensional object and then when it sees us, well, we don't have evidence. This is what you need to understand. We don't have any evidence for a 4th-dimensional object till now. I mean, if you consider the 4th dimension as space, well, 3-dimension space and 1-dimension time, if that's how you treat it as 4th dimension, yes, it is there. But what I'm talking about is higher dimension space. If you're telling about it, we don't have evidence. Okay, right. And is black hole a 4D object, right? That question is also added to that. Well, that's what I'm telling. The 4th dimension, what you're actually treating, if you're treating time, yes, every single object is basically a 4D object in that way. But other than that, we don't know about the higher spatial dimensions. They do exist or not. It could be bigger than already existing 3rd dimension, or it could be much, much smaller. Okay, it could be something very small, smaller than an atom. The 4th dimensional spatial dimension I'm talking about, it could be very, very small, curled up into a string. So that could be also a possibility.
Thank you, sir.
That was really an insightful answer, sir. So moving on to the next question asked by Arjun. He says that I read somewhere that we know data about the Big Bang only from a Planck time after it occurred. Why do we have information only from after the Planck time, and is the Planck time a limit for that?
Well, we do have data after Planck time just because that is where our non-physics will stop. Because before Planck time, if you need to know anything about it, you need to merge the 4 fundamental forces. That means basically the quantum mechanics has to merge with gravity and it becomes some kind of quantum gravity, a kind of theory of everything should be there to resolve that problem. So before the Planck time, that is 10 raised to minus 43 seconds, even though you can actually propose that concept, you can bring it up to t equal to 0. You can propose that, but we don't know whether such things exist before the blank time, or if at all it exists, how it looks like, because we haven't still combined these fundamental forces. That is why every time we explain about Big Bang, we start from blank time, and not before that. And well, there are several scientists, bringing that concept of quantum gravity and trying to propose that idea into several other hypotheses. But let's don't go into those things for time being, because physics ends up, time being, the non-physics ends up at blank time.
That was a clear explanation, sir. So the next question is also asked by the same person. It goes as, some recent hypotheses suggest that our universe might exist inside a black hole. How does this idea align with general relativity, and what evidence could support or refute it? I asked ChatGPT about this a few days ago, and it said that it's not just science fiction.
Well, okay. Well, you're dependent on an artificial intelligence concept, and maybe when quantum computer comes, just ask quantum computer also the same question. You may hear some interesting answers. Okay, whatever. The thing is, the hypothesis is like, what if our universe is inside a black hole? Now, one possible explanation why they are saying that is because if you look at the entire mass of the observable universe that we do know, and you can calculate the Schwarzschild or radius of a black hole, which is the radius of the black hole, you can calculate from the mass. Okay, so if you look at the universe, the entire mass, we know the data. Okay, and with this data, if you calculate the radius of an imaginary black hole, it comes close to that number, 46.5 billion light years. This is the reason why we are actually proposing that what if the observable universe is actually inside a black hole. It's actually interesting. Maybe it could be just a chance. Many scientists are saying that it is probably a chance only. There is no way that it can happen because inside a black hole, we have some idea that if anything falls into black hole due to its immense gravity, it should come towards the center, what we call as singularity. Well, singularity, don't misunderstand that it is a point of infinite gravity. No, it's not an infinite gravity point. It's basically a point of very high finite gravity. So if our universe is actually within a black hole, everything you see around you should come towards one central point, which is not happening. What actually happening is the universe is expanding. So that's a counter argument to say that the black hole cosmology is wrong. Okay. Now, one counter argument again, so the people who support black hole cosmology is that they do say, okay, fine, everything should come towards the center inside a black hole, which is not happening inside our observable universe. What if the observable universe that we are staying in is kind of a mirror concept of black hole, like a white hole, because the physics is allowing a white hole to exist, but we haven't just observed that. Inside a white hole, everything goes, everything expands. So when you compare with that white hole concept, it is working. I don't know how much I have actually conveyed this concept to you. But so the thing is, when you bring general relativity into it, some of its mathematical numbers or equations do support this black hole cosmology. And that is why we do propose that maybe we are stuck inside a black hole.
Thank you for elaborating on that topic, sir. I hope, Arjun, that you're satisfied with the explanation. So next we are having a thought-provoking question by Shirin. It is, what if the imperfections and flaws we observe in the universe are not random or accidental, but rather intentional design element?
Design elements, okay. Always welcome. But then I would say that it is one among the most, I would say that, okay, it could be one possible chance that everything is not random or accidental. Someone might have actually designed. Then that designer actually needs to read NCERT physics. Yeah. That's the answer for that question from my side, because you look at the designs, really look at the designs. Shirin, I would say that you look at the positions of the planets, you look at the biological evolution. There are several examples. Just this human hair. Why should there be human hair? That's the first question. Because it's a part of evolution. That's what you see. You know, if someone is actually designing a human being, they don't need to keep this human hair. They don't need to keep the tailbone. They don't need to keep the blind spot in the eye. Several flaws you can see. So you have already put the hypothesis or assumption, okay, what if these are not random or accidental? Then my answer is, okay, well, that designer needs to learn physics or biology or chemistry properly. Okay, thank you. Next one.
Thank you for connecting those concepts, sir. Next, we have something related to quantum computing. So here it goes. Hi, Paulose sir. I'm Jyotika, and we once talked more about quantum computing and string theory. Still, I believe a huge development in quantum computing can change the code of our world. So, I would like to know your opinion on the development of quantum computing that sometimes can simulate the physics of early universe to experiment on the multiverse hypothesis. Both Malayalam and English is okay for me.
Yeah, well, that is one area that we are still figuring it out, quantum computing. You know, one interesting fact about quantum computing is that people are actually afraid of quantum computers. Like, imagine a very fully functional quantum computer comes into being, that it literally decodes or decrypts the entire passwords of the entire human beings using it for their transactions and everything. So quantum computers, we have actually, overhyped that concept of quantum computers. Don't think that it can do everything. Okay, that's the first thing you need to understand. So it also has limitations. No doubt in that. It also has limitations. Quantum computers, it has to come fully functional to actually understand what is its strength and what will be its weakness. Well, we are living in the world of AI, and we know what all things AI can do. But definitely, AI is basically giving you results of what we already know. I mean, it's not giving a complete new result. It is not giving you. But quantum computers can propose new results. That is what we are actually, one way we can say we can hope for, or another word we can say we are afraid of. We are not sure. So right now, the intelligence, according to the famous scientist Michio Kaku, that the intelligence that we have designed has come up to a intelligence something similar to a cockroach. That's what he used, that word. And this intelligence of cockroach, we will design in something like, it looks like the intelligence of a rabbit. And if the intelligence, again increases to something like what we can say a monkey, then it will get that self-consciousness concept. So these monkeys know that they are completely different species. So same way, quantum computing figures out, okay, well, we are completely different species. So I know the reality about the origin of the Big Bang and the universe. Quantum computing, just imagine a quantum computer is actually thinking about it. Well, why should I share that knowledge to human beings? What if I don't share that knowledge? What if I can actually rule these human beings? Well, that is another hypothesis. We don't know. So if you think that you can actually control this entire quantum computers, then I would really suggest you to watch the latest movie of Mission Impossible series. But quantum computer itself is detaching from the human entities and getting that self-awareness and thinking something completely separately and trying to rule the entire world. So there is no turn-off button there. But yeah, as you said, if we do have control, well, it can propose new medicines for AIDS, new theories it may solve. It may give the theory of everything equation. What if it solves black hole expressions? Well, always welcome. We will wait for that. That's what I have to say about it.
That was a good one, sir. So the next question is by Devik A. Kumar. Hi, Paulose sir. I'm Devik. My question is that what is the difference between open strings and closed strings, and why do they matter in the theory?
Well, these are separates different kinds of vibrations. Well, I'm not deep into that, like the level of the knowledge that you are expecting for regarding the concepts of string theory. What I know regarding is that different possible vibrations also include open vibration and closed vibration. This is a simple way to understand that all possible vibrations, what all possible vibrations you can think about it. In that you look at it, you can see one possibility is open vibration, another possibility is closed vibration. So both kind of possibilities do exist, and the shapes at which they do vibrate, generate the basic fundamental quantities that we see around you. So what it has to matter with the theory, because any kind of vibration is basically a subatomic particle. That's how the string theory is proposing. So you take an open vibration, doesn't matter. A particular vibration, a particular way in which it vibrates, you can call it as an electron. A particular closed loop vibration, you can call it as a photon or photon. Understand? So it goes on like that. Well, all possible vibrations, if you consider, it also includes open loop and closed loop.
Thank you, sir.
So here's the next question by Adarsh. So he asked that, is it theoretically possible for two parallel worlds to interact or say leak information to each other?
Well, so suppose if we do say parallel worlds do exist, then this question arises. So we are imagining actually two parallel worlds exist. Okay, so what kind of parallel worlds you are actually thinking about? Are you thinking about two membrane layers, like membrane parallel versus other, like one membrane over the other, over the other, over the other? It goes like that. And another kind of parallel verses are like expanding universe on one side. On another side also another universe is expanding. So they may interact each other. If at all they do interact gravitationally. So definitely we get the gravitational waves. We do have gravitational detectors. We are observing that. And definitely some kind of gravitational wave, if you are detecting it, and if it is not in the list of the natural cosmic phenomena, one way we can conclude is, okay, this kind of vibration we might have got maybe from parallel verse. This is one way to understand that. So we don't know. We haven't yet received any kind of signals out from other parallel verses. We are actually listening to it.
Thank you for the explanation, sir. And now we have got another question from Shirin. So it goes as, could future discoveries in physics lead to the emergence of new fundamental laws that challenge or expand our current understanding of the universe?
Of course. Why not? There is no doubt in that. Physics has not yet stopped, I would say. If string theory exists, imagine if string theory exists, what are strings made up of? That question is there, isn't it? Which again opens another realm. And we are not even stopping in string theory. We will never stop. That's the specialty of human beings, that we keep on thinking. We are always curious to know, okay, if this thing is made up of that, then what is that thing actually made up of? So this way we keeps on going. So of course the new discoveries will obviously opens a wide area, and we will be continuously studying it, finding evidences for it, and that's because somehow we need to go out from this earth. We need to settle in other planets and all, isn't it? Because at one point we know that the sun is becoming bigger and bigger. It's changing into its red giant state, isn't it? And slowly it will be the Mercury, Venus, Earth, all will be going into that sun. Somehow we need to escape from here. We need new technology. We need new physics. So yes, definitely we'll be finding more and more stuff.
Thank you for shedding the light of clarity on that topics. So next is by Arjun J. It is quantum Zeno effect or theory, or is it a hypothesis? Because it states that when we measure the system, we force the wave function to collapse into one definite state.
Well, I'm not so sure about that word. I mean, I have heard that obviously, quantum Zeno effect, but maybe I can comment about the second statement, that because it states that when we measure the system, we force the wave function to collapse into one definite state. A kind of the basic thing that you have studied in a 12th grade physics in the chapter wave optics, if you do remember, the particle wave duality, isn't it? It's like all quantum operations that are happening all around you. The moment you try to measure it, immediately that wave function is collapsing. You can clearly explain it using Schrödinger wave equation. And the moment you measure it, only this is happening. And if you don't measure it, it's like a wave. Measure it, particle. Don't measure it, wave. So, this duality principle, and even though we call ourselves as matter, we are also actually the superposition of the subatomic wave functions, we can say. But we do see as matter itself, because when waves superimpose, you get a bigger and bigger peak. But if you look at quantum, stuffs, they do exist in that dual nature. And the moment you actually make a measurement only, that's I'm highlighting that point. If you take measurement only, immediately, that will go to a particle state. So it's like a simple way to understand is, even though this is not the best example, like if you toss a coin and there is a possibility of head and tail to be there. So until that coin comes and rests on our palm, then only we know that whether it is a head or whether it is a tail. Till then, it is in a superimposed state. Okay. So the second part of that statement, I say that yes, you need to take that measurement. Until that, it is in a superimposed state. So another good example that we can compare with classical mechanics is that imagine a person is standing behind you. Okay, imagine you need to actually look behind you to confirm that whether actually that person is there or not. Okay, so until you make the measurement, that condition of standing person is in a superimposed state. Could be there, could not be there. You need to take the measurement. But this is only an example that you can connect to classical physics, but we know that doesn't ever happen, isn't it? That's not how classical physics work. But to make quantum mechanics understand, these are some examples that we can depend on.
Thank you so much, sir, for addressing all those questions with such clarity. Now, I'd like to ask a few questions from my end based on some of the technical aspects you have touched upon during the session. May I proceed?
Yeah.
Okay, sir. So the first is on the fine-tuning thing you have mentioned. We often use fine-tune meshing parts to reduce friction and improve efficiency. If the universe constants were adjusted even slightly, as in fine-tuning, could that analogy be extended to explain why our cosmos operates so stably?
Yeah, first of all, you need to understand that tiny variations in fundamental constants are not going to make, tiny changes in the fundamental constants are not going to make a massive change like you are expecting. That is not how we need to understand. Okay, you need to check the range. Okay, for example, gravitational constant. If the value changes beyond this range, then what will happen? This is how we need to understand. But what I have heard in many videos and many debates and arguments, it's like they do say a tiny change, 1 among 10 raised to, like that they will say number, and then the universe itself won't exist like that. No, it's not like that. You need to understand that if a tiny fluctuation is happening in the gravitational constant, how it depends upon other fundamental constants, how they are going to change. We need to observe not just one fundamental constant variation, but multiple fundamental constant variations we need to observe. And then that cumulated chaotic change we need to calculate. Then only we get an idea, okay, fine. If it goes beyond this range, okay, galaxies are not going to form. Fine. But a tiny fluctuation is never, it's not going to make any effect. That's one thing. Second thing is that what if, for example, actually, there are so many papers now being published based on fine structure constant. I would like you people to just refer on that papers. I don't remember the exact names of that. So changes in fine structure constant. That's on, basically you can search for. Many scientists are proposing this idea that the fine structure constant value was actually different during the beginning of the Big Bang, which we can get it from the hydrogen spectrum. And tiny variation, very tiny variations, but it is actually within the error range. So we cannot say conclusively that actually that value has changed. And many other papers are out there that it is predicting there will be change in the gravitational constant later. Understood? Because the accelerated universe, where it is going, that one question is there. So the gravitational constant value may change later in the future. So these kind of beautiful papers are there. But tiny fluctuations is not going to end up the universe just like that. I would say that it is an evolved universe. The entire cosmos that you see is an evolved one. And I strongly believe that these fundamental constants are not designed. They have come to that values depending upon many other physical parameters.
Okay, so like basically you're saying that we can't connect this thing with the that weather prediction thing, where even the small changes in the decimals can bring vast difference in the weather predictions, randomness.
Yeah.
So this
There
can
should
be
be a
connected
range.
with that.
Correct. There should be a range. Like there is a huge cyclone. Okay, imagine.
Okay,
And
sir.
what if I keep my cup from here to the other side? Is it going to affect the cyclone? No. What
No,
if a
actually.
few dust particles change its spatial position? Is it going to end the cyclone? No. So there is a range. Understand?
Mhm.
There has to be a range, and within that range, if the physical parameters change, well, cyclone itself may stop or it may increase its intensity. So we need to work on that range.
Okay, so so the next question is, in mechanical systems, resonance can amplify vibrations drastically. Could there be a higher dimensional equivalent, a sort of dimensional resonance that amplifies certain cosmic phenomena?
Can you read that second part? It was not clear.
Okay. Could there be a higher dimensional equivalent, a sort of dimensional resonance that amplifies certain cosmic phenomena?
Okay, well, the best answer is I don't. That's the best answer to say that whether they do exist or not. First of all, we don't know whether higher dimensions exist or not because we don't have evidence. What if they exist? That is a different question. But as of now, we don't have any single clue regarding the higher dimensions. And again, if they do exist and their vibrations, some people do say, since you have said this, recently in a program, I heard that you can actually telepathically connect your brain with other people through higher dimensions. Have you heard about these kinds of claims?
Yeah.
Right?
Yes,
You
yes,
are
yes.
sitting in India. Maybe your friend might be sitting in Canada, and then you decided to call her. Suddenly, the call came here. Okay,
Yeah.
and her call is coming right at your phone, and through telepathy you communicated, and that communication happened through higher dimensions, through some kind of vibrations. Never ever. That's not going to happen. That's not science works. Now you imagine about Sachin Tendulkar. Okay,
Mhm.
few years you keep on thinking about Sachin Tendulkar. Let's see whether he calls or not. This is how probability works. Well, your friend, there is a very high chance for your friend to call you. Okay, and
Mhm.
it's very, very low probability for Sachin Tendulkar to call you. Maybe, I don't know. If you have connection, he may call, but I'm just randomly picking some name. So it is very low probability chance for him to call you. What I'm trying to say is that these kind of higher dimensional stuffs that we do simply in simple language nowadays we explain everything through scientific words, even if you don't know anything. So you have to be very careful. Understood? So, well, we don't know about higher dimensions, so I can't comment on that.
So just now something came to my mind that have you heard about the Simpsons cartoon, sir? The Japanese cartoon which had so many future predictions.
Oh, yeah.
So is it also something related to this, or was it a random thing of a probability?
I would say, like, you make a cartoon, okay? You make a cartoon that 10 possible situations can happen. Like, okay, an asteroid coming and hitting, okay? And then different 10 possibilities. And Simpsons cartoon series is not one single cartoon. It has been over years. They have been, broadcasting these kinds of cartoon series. So obviously it's like a cherry picking. Understood? So something, if it happens right around you, we immediately connect it with Simpsons cartoon